Hello, this is Sydney Micah, and I will be talking about light and atomic emission spectra. The quantum mechanical model grew out of the study of light, so let's begin by investigating the nature of light. Light consists of waves. As shown in this diagram, each complete wave cycle starts at 0 on the y-axis, increases to its highest value, passes through 0 to reach its lowest value, and returns to 0 again. The amplitude of a wave is the wave's height from 0 to the crest. The wavelength is the distance between the crests. The frequency is the number of wave cycles to pass a given point per unit of time. Frequency is usually measured in cycles per second. The SI unit of cycles per second is called the hertz. As wavelength of light increases, frequency decreases. Light consists of electromagnetic waves. Electromagnetic radiation includes radio waves, microwaves, visible light, and gamma waves, to name a few. The sun emits white light, which consists of light with a continuous range of wavelengths and frequencies. When sunlight passes through a prism, the different wavelengths separate into a spectrum of colors. When electric current passes through a gaseous element or through the vapor of a liquid or solid element, the electrons of the atoms are energized. When atoms absorb energy, their electrons move to higher energy levels. These electrons lose energy by emitting light when they return to lower energy levels. Since energy cannot be created or destroyed, electrons emit the same amount of energy they absorb. When the light emitted from these electrons passes through a prism, the spectrum consists of a limited number of narrow lines of light. The wavelengths of these lines are characteristics of the element. They make up the atomic emission spectrum of the element. No two elements have the same atomic emission spectrum. Therefore, this characteristic can be used to identify elements. The product of frequency and wavelength equals the speed of light, which is constant. We can use this equation to calculate the wavelength of light. Sample problem 5.2 asks us to calculate the wavelength of the yellow light emitted by a sodium lamp if the frequency of the radiation is 5.09 times 10 to the 14th. Since we know the frequency and the speed of light, we must solve for the unknown wavelength. I started this problem by filling in what we know, the speed of light and the frequency. Then I divided both sides by the frequency so it would cancel. After some division and canceling, I was left with 5.89 times 10 to the negative 7th meters. Don't forget to leave your answer in significant figures.
Hello, this is Olivia Phillips, and I will be talking about the quantum concept and photons. According to classical physics, the atomic emission spectrum of an element should be continuous. This does not explain the emission spectra of atoms, which consist of lines. In 1900, German Max Planck was trying to describe why a body goes from black to red to yellow to white as temperature increases. He found he could explain the change by assuming the energy of the body changes in small discrete units, or quanta. He showed mathematically that the amount of radiant energy, represented by a capital E, of one quantum absorbed or emitted by a body is proportional to the frequency of radiation, as seen in this equation. The energy of a quantum equals h times v. The constant h has a value of 6.626 times 10 to the negative 34th joules times seconds and is called Planck's constant. Albert Einstein used Planck's quantum theory to explain the photoelectric effect. In this effect, electrons are ejected when light shines on a metal. A specific frequency is required for this to take place. To explain this effect, Einstein proposed that light could be described as quanta of energy that behave as if they were particles. These light quanta are called photons. The energy of photons is quantized according to the equation E equals hv. Based on this theory, we must consider that light has both wave-like and particle-like properties. Sample problem 5.3 asks us the energy of a photon of microwave radiation with a frequency of 3.20 times 10 to the 11th per second. Using this given frequency and Planck's constant, we can follow the equation here. When we fill in the values we know and solve, we get 2.12 times 10 to the negative 22nd joules. This makes sense because individual photons have very small energy.
Hi everyone, I'm Tegan Sweet, and I will be talking about an explanation of atomic spectra. Atomic emission spectra were known before Bohr proposed his model of the hydrogen atom. Bohr applied quantum theory to electron energy levels in atoms to explain the atomic emission spectrum of hydrogen. His model explained why atomic emission spectrum of hydrogen consists of specific frequencies of light, and predicted these frequencies. In the Bohr model, the single electron in hydrogen can have only specific energies. When the electron is at its lowest possible state, the atom is in its ground state. Principal quantum number is represented by variable n. Excitation of the electron by absorbing energy raises the atom to state n2, 3, 4, 5, 6, and so on. Electronic transition is the single-step emission of energy in the form of light when the electron drops back to a lower energy level. Bohr knew that this quantum of energy E is related to the frequency V of emitted energy light by E equals hv. Light emitted by an electron moving from a higher to a lower energy level has a frequency directly proportional to the energy change of the electron. This diagram shows the three groups of lines in the emission spectrum of hydrogen atoms. Notice that the spectral lines in each group become more closely spaced at increased values of n because the energy levels become closer together. Bohr's model explained the atomic emission spectrum of hydrogen, but not the emission spectrum of atoms with more than one electron. Also, it did not help in understanding how atoms bond to form molecules.
Hi, this is Caroline. I'm going to talk about the quantum mechanics recap section.
In the first section, Sydney talked about light and atomic emission spectrum. We learned that light consists of waves. The amplitude is the wave's height from zero to the crest, and the wavelength is the distance between two different crests. Frequency is the number of wave cycles to pass a given point per unit of time. The SI unit of this is hertz. We also learned that as a wavelength of light increases, the frequency decreases. Light is made up of electromagnetic waves. Electromagnetic radiation includes radio waves, radar, gamma rays, and visible light, just a few examples. The sun releases white light. White light consists of light with a continuous range of wavelengths and frequencies. Sydney told us that when sunlight passes through a prism, its wavelengths separate into a spectrum of different colors. When an electric current passes through a gaseous element or through the vapor of a liquid or solid element, the electrons are energized. When atoms absorb energy, their electrons move to higher energy levels. These electrons then lose their energy by emitting light and returning to lower energy levels. This light emitted from these electrons passes through a prism. The spectrum that is created can only consist of a limited number of narrow lines of light. The wavelengths of these lines are characteristics of the element and make up the atomic emission spectrum of the element. This atomic emission spectrum is very important because it can be used to identify the elements. Lastly, Sydney told us that the product of frequency and wavelengths equals the speed of light. This speed of light is also constant. Second, Olivia talked about the quantum concept of photons. In 1900, Max Planck determined why the body changed color when the temperature increased. His reason was that the body changed in quanta, or small discrete units. Mathematically, he showed the amount of radiant energy of one quantum absorbed or emitted by a body is proportional to the frequency of radiation. This is shown in the equation E equals hv, E being the energy of quantum and V being the frequency. This constant h, known as Planck's constant, is equal to 6.626 times 10 to the negative 3/4 joules times second. Olivia also explained that Einstein uses quantum theory to explain the photoelectric effect. The photoelectric effect is when electrons are ejected when light shines on a metal. This requires a specific frequency, though. To explain this, Einstein proposed that light could be described as a quanta of energy that behave as if they were particles. This light quanta is called a photon. Because of this theory, light has both wave-like and particle-like properties. Lastly, Tegan talked about atomic spectra. We learned that Bohr utilized quantum theory to electron energy levels in atoms to explain the atomic emission spectrum of hydrogen. In the Bohr model, the single electron in hydrogen can only have specific energies. When the electron is at its lowest possible state, it is at ground state. The principal quantum number is the variable n, and the excitation of the electron by absorbing energy raises the atom to state n equals 2, 3, 4, etc. Tegan also said that the electron transition is a single-step emission of energy when the electron drops back to a lower energy level.
Bohr used Planck's quantum theory to state the light emitted by an electron moving from higher to lower energy levels has a frequency directly proportional to the energy change of an electron. In this diagram Tegan used, she said that spectral lines in each group become closely spaced at increased values of n because the energy levels become closer together. You can see this in this diagram.
And that is quantum mechanics. Thank you for listening.